Aim: to draw IV characteristics of the junction diode. The apparatus used in this experiment are a PN junction characteristic apparatus and connecting wires. A P-type semiconductor is the one which has free hole and impure immobile negative ions. So, we can say that P-type semiconductor have excess number of holes and they are majority charge carriers. Whereas N-type semiconductor is the one which has free electron and impure immobile positive ions. So, we can say that N-type semiconductor have excess number of electrons and they are the majority charge carriers. The combination of P-type and N-type semiconductors result in a PN junction diode. Here, at the junction, diffusion takes place. Similarly, due to the higher concentration of electrons in the N section, electrons diffuse from N side to P side, leaving behind an ionized positive charge which is immovable. As the holes and electrons continue to diffuse, a layer of negative charge on the P side of the junction and a layer of positive charge on the N side of the junction is developed. This junction region is known as depletion layer. Since either side of the junction region stationary positive and negative charges exist, there is an electric potential difference Vd across the junction which is called potential barrier. It prevents the further movement of holes and electrons. And this whole combination is nothing but the PN junction diode. Here, the white line on one end indicates that it is a negative terminal. Now, let us study the forward bias characteristics. When P section is connected to the positive terminal and N section is connected to the negative terminal of the battery, the PN junction is said to be in the forward bias. With the increase in forward bias voltage, the forward current increases slowly. When the forward bias voltage V equal to the threshold voltage, the forward current increases rapidly. Now, let us move on to the reverse bias characteristics. When the P section is connected to the negative terminal and the N section is connected to the positive terminal of the battery, the PN junction is said to be in the reverse bias. With the increase in the reverse bias voltage, a very small reverse current flows which remains almost constant. When the reverse bias voltage V equal the reverse breakdown voltage, the reverse current suddenly increases to a large value. N junction diode, forward bias. Range of the voltmeter is equal to 0 to 1 volts. Least count of the voltmeter is equal to 0.02 volts. Zero error of the voltmeter is equal to nil. Range of milliammeter is equal to 0 to 15 milliamperes. Least count of milliammeter is equal to 0.3 milliamperes. Zero error of the milliammeter is equal to nil. Observation table for forward bias voltage and forward current. When the input voltage Vf is increased in steps of 0.02 volts from 0 to 0.2, the forward current If is 0. After that, when the input voltage is increased in steps of 0.1 volt, the input current slowly increases. Using the values of forward voltage and forward current, we plot a graph by taking forward voltage on x-axis and forward current on y-axis. We consider a suitable scale. On x-axis, 1 cm is equal to 0.1 volt. On y-axis, 1 cm is equal to 5 milliamperes. Origin 0, 0. Now, let us plot the points on the graph. The graph comes out to be as shown here. In forward bias, junction resistance is R is equal to delta Vf by delta If, which is 0.7 minus 0.6 by 15 minus 5. That is equal to 0.1 volt divided by 10 milliamperes is equal to 10 ohms. Junction resistance for forward bias is 10 ohms. Reverse bias. Range of the voltmeter is equal to 0 to 100 volts. Least count of the voltmeter is equal to 2 volts. Zero error of the voltmeter is equal to nil. Range of the microammeter is equal to 0 to 100 microamperes. Least count of microammeter is equal to 2 microamperes. Zero error of microammeter is equal to nil. Observation table for reverse bias voltage VR and reverse current IR. When the reverse bias voltage is 4 volts, the reverse bias current is 2 microamperes. Similarly, the reverse bias voltage is increased and the corresponding reverse current readings are as follows. Using the values of reverse voltage and reverse current, we plot a graph by taking reverse bias voltage along negative x-axis and reverse bias current along negative y-axis. We consider a suitable scale. On x-axis, 1 cm is equal to 10 volts. On y-axis, 1 cm is equal to 20 microamperes. Origin 0, 0. Now, let us plot the points on the graph. The graph comes out to be as shown here. Let us consider 2 points A 3018 and B 4032 in the graph. In reverse bias, junction resistance is R is equal to delta VR by delta IR, that is equal to 40 minus 30 by 32 minus 18, which is 10 volts divided by 12 microamperes. That is 0.83 into 10 power 6 ohms. Therefore, junction resistance for reverse bias is equal to 0.83 into 10 power 6 ohms. All connections should be neat, clean and tight. Key should be closed only when we are taking the readings. The voltage should be increased in steps of 0 to 1 volt until you observe a significant change in the current. Forward bias voltage beyond breakdown should not be applied.